Chapter 6, Momentum. This lecture will help you understand momentum and impulse. Momentum is a commonly used term in sports. A team that has momentum is on the move and is going to take some effort to stop. Momentum is also a physics term. It refers to the quantity of motion that an object has. If an object is in motion, on the move, then it has momentum. We learned in previous chapters that we can relate motion, velocity, and acceleration of objects, and none of the formulas developed required the use of mass of an object. A ping pong ball moving at 40 miles per hour is the same as a car moving at 40 miles per hour. But which one would you rather get hit by, the ping pong ball or the car? You inherently know that mass plays some role in the motion of an object. Momentum can be defined as mass in motion. All objects have mass, so if an object is moving, then it has momentum. The amount of momentum that an object has is dependent upon two variables: how much stuff is moving and how fast the stuff is moving. Momentum can also be defined as the inertia, a measurement of an object's tendency to continue in motion at a constant velocity. The momentum of the object is equal to the mass of the object times the velocity of the object. Symbolically, we give momentum the letter P and write P equal m times v, where m is the mass and v is the velocity. The equation illustrates that momentum is directly proportional to an object's mass and directly proportional to the object's velocity. Like velocity, momentum is a vector. Mass is a scalar and velocity is a vector. Momentum, therefore, is a vector quantity. Momentum then has the same direction as the velocity. It is a scaled version of the velocity v. Watch the Bill Nye video on momentum on Blackboard. When the speed of an object is doubled, its momentum A remains unchanged in accord with the conservation of momentum, B doubles, C quadruples, D decreases. Answer is B, doubles. Momentum is directly proportional to an object's velocity. For example, find the momentum of a 1,350 kilogram car moving at 75.0 kilometers per hour. We first write down what we know: the mass of the car at 1,350 kilograms and the velocity of the car that we need to convert to meters per second. And we get 20.8 meters per second. Our working equation is the same as the basic equation, the definition of momentum. Substituting what we know, we get 28,100 kilograms meters per second. The units of momentum are kilograms meters per second. Find the velocity of a 1.00 times 10 to the minus 2 kilogram bullet so that it has the same momentum as a lighter bullet of mass 1.8 times 10 to the minus 3 kilograms and a velocity of 325 meters per second. We first find the momentum of the lighter bullet. Using the subscript L to indicate the lighter bullet, we know its mass and velocity and get 0.585 kilograms meters per second. We know the mass of the heavier bullet, but do not know the velocity. The basic equation is the definition of momentum with the subscript H, indicating the heavier bullet. But we know the momentum of the heavier bullet is the same as the lighter bullet, so we set pH equal to PL. Solving for our velocity, we get 58.5 meters per second. A large truck has more momentum than a car at the same speed because it has a greater mass. Which is more difficult to slow down, the car or the large truck? The truck, but why? To understand the reason, we introduce a new concept. We use the delta notation to indicate change in a quantity. Delta P means P final minus P initial. The final momentum minus the initial momentum. We define momentum in terms as before, the mass times the velocity. To be fair, a change in momentum can mean either a change in mass or a change in velocity, or both. That is why the final and initial subscripts are used on both the mass and velocity. Any object with momentum is going to be hard to stop. The more momentum that an object has, the harder that it is to stop. To stop such an object, it is necessary to apply a force against its motion for a given period of time. Forces are not applied forever. They are only applied for a certain amount of time. In Newton's second law, we learned that acceleration is the force divided by the mass. We also learned from kinematics that the acceleration is the change in velocity over the change in time interval. Equating the two gives F over m equals delta V divided by the time interval. The force times the time interval is equal to the mass times the change in velocity. If we realize that m delta V is just the change in momentum, if the mass is constant, we get the force times the time interval equals the change in momentum. Newton actually formulated the second law in terms of change in momentum and not acceleration. We now define impulse and give it the symbol J. The impulse J of a force is the product of the average force and the time interval, delta t, during which the force acts. Impulse is a vector and has the same direction as the average force. The SI units of impulse are the Newton second. Impulse is the product of force and contact time. Equation: the impulse is force times the time interval. A great force for a long time provides a large impulse. The same force for a short time means a smaller impulse. Watch the impulse momentum theorem video on Blackboard. When the force that produces an impulse acts for twice as much time, the impulse is A, not changed, B, increased by 2 times, C, increased by 4 times, D, decreased by half. Answer is B, increased by 2. Impulse is directly proportional to the force. Impulse changes momentum. The change in momentum of an object is equal to the impulse applied to it, force multiplied by the time interval, during which the force is applied. Force times the time interval equals the change in momentum. Cases of momentum changes occur when you apply great force for a long time, which produces a great increase in momentum. An example: golfer follows through while teeing off, long barrels of long-range cannons, and the follow-through when you swing a bat. A 17.5 gram bullet is fired at a muzzle velocity of 582 meters per second from a gun with a mass of 8.00 kilograms and a barrel length of 75.0 centimeters. A, how long is the bullet in the barrel? B, what is the force on the bullet while it is in the barrel? C, find the impulse exerted on the bullet while it is in the barrel. And D, find the bullet's momentum as it leaves the barrel. To find the time the bullet is in the barrel, we resort to our familiar kinematic equations. We know the length of the barrel, 75 centimeters. We know the final velocity as the bullet leaves the barrel, the muzzle velocity of 582 meters per second. And we know the initial velocity. The bullet started from rest, so must be equal to 0. The average velocity can be found to be 291 meters per second. The distance traveled is the average velocity times the time interval. Solving for the time interval, we find the length of time in the barrel is 0.00258 seconds to 3 significant figures. To find the force, we need the time interval, the bullet mass, and the initial and final velocity. The force can be found using the impulse equation, yielding a force of 3,950 newtons. The time interval and the force is known. The impulse is the force times time interval, yielding an impulse of 10.2 kilograms meters per second. The momentum as the bullet leaves the barrel is the mass times the muzzle velocity. Both these quantities are known. The momentum is then 10.2 kilograms meters per second. Notice that since the initial velocity is 0, the change in momentum is equal to the impulse. This is always true. A cannonball shot from a cannon with a long barrel will emerge with greater speed because the cannonball receives a greater average force, impulse, both of the above, neither of the above. The answer is B, impulse. The force on the cannonball will be the same for a short or long barreled cannon. The longer barrel provides for a longer time for the force to act and therefore a greater impulse. The long barrel also provides a longer distance that the force acts, providing greater work and greater kinetic energy of the cannonball. When momentum decreases, it can be applied over a short time or a long time. Decreasing momentum over a longer time results in smaller force. Driving into a haystack versus driving into a brick wall. Jumping into a safety net versus jumping onto solid ground. When a car is out of control, it is better to hit a haystack than a concrete wall. This is common sense, but it has a physics reason. The same impulse occurs either way. It is the same change in momentum. But by extending the contact time, you reduce the force of impact. In jumping, bend your knees when your feet make contact with the ground because the extension of time during your momentum decrease reduces the forces acting on you. In boxing, ride with the punch. Automobiles have crumple zones and airbags to increase the contact time and decrease the amount of force felt. From the impulse equation, solve for F by dividing both sides by delta t. For a given change of momentum, if the time interval is short, the force is large. When the time interval is long, the resultant force is small. Decreasing momentum over a short time interval produces a large force. For example, Casey splits a stack of bricks by bringing her arm and hand swiftly against the bricks with considerable momentum. The brief contract imparts a huge impact force. Would you rather be in a head-on collision with an identical car traveling at the same speed as you or a brick wall? Assume in both situations you come to a complete stop. Take a guess. The answer is, it does not matter. Look at our impulse equation. F delta t is m delta v. In both situations, delta t, m, and delta v are the same. Hitting a brick wall results in the same impulse, change of momentum as hitting another speeding car. If the choice is hitting a car head-on or the back of a truck heading in the same direction as you, aim for the truck. Since the truck is moving in the same direction, the time of impact will be lengthened, lowering the force you feel. An egg dropped on the tile floor breaks, but an egg dropped on a pillow does not. Why? Again, F delta T is M delta V, our impulse equation. In both cases, M and delta V are the same. If delta T goes up, what happens to the force? Right, the force goes down. When dropped on a pillow, the egg starts to slow down as soon as it touches it. A pillow increases the time the egg takes to stop. In NASCAR, they use a safer barrier, steel and foam energy reduction, during a high-speed crash. It lengthens the time of impact and decreases the force felt by the driver. A fast-moving car hitting a haystack or hitting a cement wall produces vastly different results. Both experience A, the same change of momentum, B, the same impulse, C, the same force, or D, A and B. Answer is D, both A and B. Although stopping the momentum is the same whether done slowly or quickly, the force is vastly different. Be sure to distinguish between momentum, impulse, and force. When a dish falls, will the change momentum be less if it lands on a carpet than if it lands on a hard floor? Careful here. A, no, both are the same. B, yes, less if it lands on the carpet. C, no, less if it lands on a hard floor. D, no, more if it lands on a hard floor. Answer is A. Both are the same. The momentum becomes zero in both cases, so both change by the same amount. Although the momentum change and the impulse are the same, the force is less when the time of momentum change is extended. Be careful to distinguish between force, impulse, and momentum.